Hi. The task here is to right justify some text and truncate it on the left if it's too wide. If you want to read the full description here, then you can pause the video. Okay, let's start with a very simple example. This is just a character vector, and we're going to build a little lambda, a function that takes the right argument, represented with the letter omega, that's the rightmost letter of the Greek alphabet. Not much going on here. Now, the important part is that we have to handle a lot of different types of data. So we need to normalize the incoming data. We can do that using a very convenient little function, which is just like enclose, which wraps this simple character vector in an outer array, but it only does so if it's not already nested. So if we were to give multiple elements of character vectors, then it wouldn't do the enclosure. And we can illustrate this. So here we have it enclosed. If we give it multiple things, like this, then we can see how it's already nested, and this does not do any further action. So let's go back to our simple character vector. Now we have this for later, and we know that we've got one level of nesting. We need to take a left argument, let's say 5, and that is both the width of the final result, but that's also the how much we should truncate to. And we need to right justify, so that means we need to truncate on the left. That is, we want to preserve on the right, also known as to take from the right. And there's a take function in the APL. In order for it to take from the right, we need to negate the left argument. So we do that. And then we needed to apply to each of the arguments or each of the elements on the right. So in this case, there's only one, but that's fine. So we can see that gave us Urson. And finally, we need to stack on top of each other the individually truncated results if there are more. So we do that with the mix function that combines a nested array into a flatter array. And that looks very simple. If we try it with multiple, then we can see that it does the right thing as well. Now, it's also interesting to think about what happens with a single scalar, because that cannot just be enclosed. But it really works according to the spec very nicely, because it just stays the way it is, and then we take from each, that makes it into a vector, and then we remove that enclosure if there is any. So we can see this happening here. We pad it with spaces. That's what the take function does if there isn't enough data on a character data. And then the mix takes care of that extra enclosure, and we get a vector like we were supposed to get. So this just works. This is a very nice, easy to understand solution. Let's call that F. However, it isn't the most optimal solution when it comes to performance, because it uses these nested arrays and modifies these nested arrays, looping over them with the each operator. And in general, that's an anti-pattern in APL. Let's see if we can do better. Of course, the argument we get in is already potentially nested. We can't change that. But we can try to get rid of that nesting as soon as possible. So instead, we're going to take that argument here. We're going to do the conditional nesting again to normalize, but this time we're going to take advantage of mix padding short elements. However, the padding would happen on the right, which is not what we want. We want it on the left. So we can do this by reversing every element first, and then we do the mix, which does a padding, and then we reverse the whole result back again. And that gives us what we want, but it's not, it's when it comes to justification, but not when it comes to the truncation. So all we need to do now is the truncation. We could negate the left argument and then do a take. But this time we don't want to take from the rows of the result, a matrix. We want to take on the individual rows. And that means we want to apply it to vectors. Those are rank 1. So we do a take rank 1. This could work. However, since we're already doing this reversal, then this reversal happens on the entire data, and then we truncate. It would be more efficient if we could first truncate our data and then reverse a lesser amount of data. So let's wait with that over here. Now all our data is in reverse, which means we need to take from the left instead of from the right. And then we can do the reversal at the end. This gives us our result as well. So let's try to compare these. Let's call this G. Let's copy in the CMPX, the compare execution facility, from the defense workspace. And then we are going to construct some sample data. Of course, 3 words is not enough to notice the difference here. So let's take the alphabet. And from the alphabet, the entire alphabet, we enclose that. We're going to take over and over again a prefix of the alphabet with some random numbers. So these are 100 random numbers of length 10. No, 100 random numbers would be like this. So these are 100 numbers that are 10, and then we change them into random numbers from 1 to 10, and we use that to take from the entire alphabet. Now I don't want to print all of that to the screen. Let's get the first 10 of that. So we see some words of various lengths. Of course, it doesn't matter what the actual letters are, which is why we're just using the alphabet here. Good. Let's give this a name. Words. And then we can use the compare execution facility to do a 5 F words and a 5 G words and see what the execution looks like. Give this a moment. And, well, that's significant, and we're only talking about 100 words here. If you were to increase the number of words, then and maybe their length, this would potentially give us even greater speed up. Can we do better? We can, but it will get a little bit involved. Let's try this. So we want to take those words, we want to normalize them into a list of words in case there's only one. And we want to get rid of the nesting as quickly as possible. So we want to do this mix. Now, however, we lose the information about how long they are. They could have potentially spaces at the end, and that information would be lost. So we do need to access the lengths of the individual words in this nested list. Now we know that it's nested. All we want to do then is, if we just take this as an example, is we want to do a rotation. We need to rotate these letters into the right position where we can then chop accordingly. So, how much do we want to rotate them? Well, we want them to be aligned such that the longest word stays in place, and every letter gets every word gets rotated to the right by as much as the difference is between its length and the longest word's length. So we can express that rather directly here. We're going to rotate this. So the way rotate works when we already have a matrix, because we're mixed, is it rotates each row separately, which is exactly what we want. And the amount that we want to rotate by depends on the length of each word. So this is now a fork. So this gets applied to this nested array, and this gets applied. This gives us the lengths of each to this nested array. And then we use the result to rotate by. Of course, this isn't right. We don't want to rotate by the length of each. We want to rotate by a function of the length of each, which is the identity, those lengths, minus the length of the longest one. This is a maximum reduction. So now we have rotated everything to the right to justify them, but staying flat. The only step that's missing now is the truncation, which we know how to do already. There we have it. Yes, it's a bit involved. Let's see if it paid off. Let's do CMPX with F on the words and G on the words and H on... Ooh, I misnamed this. Should go up and fix that. We still want this one. And then this one should be H. We go H on the words. That happens because I forgot the left argument. And we'll try again. Now we're talking. This is only for 100 words. If it was larger amount, we would save a lot more. So sometimes you have to weigh off, you want to keep the code simple, or do you want to keep everything as flat as possible and in order to get maximum performance, or could you find some kind of balance in between that's good enough performance while keeping the code reasonably simple? So these were our solutions that we had. And we can see that, yeah, maybe this is good enough for your needs, but with some reasoning, you can find the ultimative flat solution. Thank you for watching.